So there are some kind of calculations you might be able to do on your normal computer. It might be a more powerful one, it may have 8 cores, a GPU or whatever. But then there are large calculations that can't be done on a normal computer, like powerful and big molecular dynamic runs, or ab initio calculations, CFD. There are many times where you need a hugely and massively powerful computer, and they are usually huge computers. Now, this kind of very big and very powerful computers are often called HPC clusters, HPC computers, so high prestation computation computers. Now, they actually don't have more powerful CPUs than the one of a normal computer. Maybe they might have, but it's not really the important thing behind it. The fact is that they are very distributed. They have a very distributed calculation power. So they might have even low power CPUs, but they have thousands and millions, often millions of them, that can work in the same moment. Of course, how they are stuck together is not trivial, and in order to do a program that works properly on this kind of architectures can only be done by knowing how they work and how they are done. Supercomputers are going more and more in the direction of parallelism, having plenty of parallel jobs that go on not too powerful CPUs or even on accelerators like GPUs. If you look in the top 500 nowadays, all the top computers are GPU accelerated. So, as said, very parallel, not too powerful in the single calculation unit, but simply the fact that you have millions and millions of them. So, how are they done? It's easy. You have, of course, your computer, and your computer is usually divided in nodes. That a node is alone a computing part with that is autosufficient, because usually a node is done by a RAM, CPUs, and very often in modern computers, but it's not necessary, some kind of accelerator like GPUs, that are the graphic units. So they are like independent computers. More or less that's what you can find in a normal home PC or in a laptop. A RAM, some CPUs, maybe a GPU. Now, sometimes these nodes are actually, in this aim to going more and more parallel, divided in sockets. So in this case, in each node you have more sockets, and each socket will be a unit like this. RAMs and CPUs between the same socket might or might not be linked together with a faster technology for information transfer. It depends on how the computer has been done. And then, as said, in each node or socket, depending how the computer has been done, you will have a RAM that will be linked in a very fast way with this with the CPUs inside it, and this part will be linked to a GPU, sometimes, not always, and GPUs actually are done by a massive amount of very simple and quite rudimental CPUs, and it will have its own small RAM, its own small memory that will be much smaller than the one we have for the CPUs. It's usually quite small, so when you have to use GPUs you will always have to only transfer the kind of information you really need, and this transfer can be a bit slow, so you need to optimize this process. So yeah, actually what a GPU does is doing an insane amount of very simple calculations in the exact same moment. That's the power of GPUs. So, as said, why is it so important to know this division? the fact that we have multiple nodes, and so that not each GPU is linked in the same way to each other, and that each group of GPUs has its own RAM, and that there is not one very huge, massive, powerful memory RAM in the middle of the computer where everything is attacked. Simple. This connection is very, very fast. So if I have to bring information from here to there, from my CPUs and my RAM, it's very fast. And my RAM, these CPUs can take information from everywhere and put it everywhere here with the same speed. So I don't really have to worry about how they're using this information, if this CPU can read what this CPU has written here. It's really not important. They can do whatever they want. In fact, inside this kind of structure, you usually use OpenMP to parallelize on this kind of structure. While if you had different nodes, let's not consider sockets, but they're very similar, so it's not so important, you will have a much slower connection with the other one. So if I have to move one information from this RAM to RAM 2, or memory 2 if you prefer, if I have to move something from here to here, that's incredibly slower than moving informations inside here. So I will have to optimize it. Do I really have to save something here? Do I really have to read something from here? If yes, okay, we are doing it, but you have to do it only as little as possible, and usually the trick is to mask it behind some calculations. In this way you will never have some CPU or GPU simply waiting for your information and not working for you, because you're still going to pay or this calculation time to the owners of the CPU of the HPC cluster. So to make this kind of information, you will program in an MPI style. MPI gives you a low-level control on where the informations are moved, who can read what, because as said, you can simply say that these CPUs cannot touch this RAM. Absolutely, they cannot put stuff randomly here. But only information you decide can go from here up and down. In this way you optimize it, because if you give these CPUs the possibility to do whatever they want with this RAM, you will have a huge amount of memory transfer here that is completely unnecessary and slow. In fact, OpenMP considers the memory as shared. So all the CPUs can use all the memory you give to OpenMP. And so they will put things randomly. There will not be a true ratio behind it. And that's okay if it's all in the same RAM, in the same memory. But if you give to our OpenMP two different memories, the CPUs won't be able to distinguish between them. So you will have random information going up and down. And you don't want it. While by MPI, every CPU or group of CPUs will have only one piece of memory. They can read only that, write only on that, and they know nothing about the rest. And you are the one deciding if an information goes up and down. So it doesn't always make sense if you have only one memory, and it makes a huge sense if you have multiple. To make an example of why it's important, as I said, to know how this works and the difference between MPI and OpenMP can be said easily with this small thing. During a programming course I did, I remember that I spoke with someone who simply said that he didn't understand why. By using some kind of MATLAB function, I never used MATLAB, so I don't know what exactly he was using, that should have parallelized his code. His code was still faster on his small computer than on the big cluster he had in his company. It's okay, if you use too many CPUs, you will start having some overhead and will actually lose prestations. So you might say, okay, he used too many of them. But actually, probably it might not have been the case, because maybe he used some kind of function that used an OpenMP method, method, a shared memory method, instead of a message passing method. And so actually he had all this kind of strange information movements from one memory to the other that was incredibly slow. So he probably had to read better the documentation and understand that that wasn't the right function to use in that specific situation. I said, I don't know the name of the function, but I remember he told me about it. And I think he wasn't even the only one talking me about this. So I said, writing programs for HPC clusters is quite different than writing programs for normal computers. You might need to do some things that are architecture dependent, so your program might need some modifications if you want to go to different architectures, depending on how much you optimized it for the specific architecture and how many differences there are between them. And in general, you might need to do a different program for a normal computer that has only one node, so where maybe you don't need MPI, and a HPC cluster where you will for sure need MPI. In fact, MPI is a bit tricky to insert inside on a normal, a sequential program. You often have to rewrite it from scratch, while OpenMP is quite easy to put inside a normal program and so have it working both on serial and on parallel. I hope you enjoyed the video. All the sources and the materials I used to do it are written in the description below. And here is some more content for you. But wait, don't click on it yet. First, remember to leave a feedback in the comments section to let me know what you think about it. Like, subscribe, follow me on social media, links in the description. And if you would like to support the channel, consider to donate on Patreon. Again, link in the description below. See you next time. I'm Maurice Karnbrook for the Computational Chemist.